Good day, everyone. Today, I am presenting my 3D graphics project, which is a Roblox-style 3D hollow square rendered using Python OpenGL. This program displays a 3D Roblox-style hollow square that the user can manipulate in real time using the keyboard moving, rotating, scaling, and reflecting the shape. Original object. The shape is constructed manually using OpenGL's vertex commands. Each point of the object is defined in 3D space using GL vertex 3 fx, y, z. The object consists of an outer square, an inner cutout square depth, which makes it a 3D solid instead of flat. This gives a simple but recognizable 3D model that is easy to manipulate. Transformations and controls. My program lets the user transform the object in real time using the keyboard. Translation, movement. WASD, move the object up, down, left, and right. Q and E, move it forward and backward. This is done using GL translate for RTX, TIE, TIS. Rotation, arrow keys rotate around the X and Y axis, C and V rotate around the Z axis. This is achieved using GL rotate F, angle, axis X, axis Y, axis Z. Scaling, Z scales the object up, X scales it down. This uses GUL scale for S, X, SY, SZ. Mathematics behind the transformations. All transformations in OpenGL are based on 4x4 transformation matrices. These matrices are multiplied with the coordinates of the object to produce a new transformed position. Translation matrix moves the object by TX, TY, TZ. Rotation matrices. There are different rotation matrices for rotating about the X, Y, or Z axis. Scaling matrix multiplies the size of the object in each dimension. Reflection. Reflection is simply scaling one axis by -1. Each vertex of the shape is multiplied by these matrices, and the final result determines where the point appears in 3D space. How transformations are applied. In OpenGL, all transformations are combined into a single model matrix. This model matrix is applied to every point of the object. Final position equals model matrix times original position. This means the order of transformations affects the final result, just like multiplying matrices in mathematics. Final output, when the program runs, the user sees the 3D Roblox-style object on-screen text showing controls. Real-time updates as the object moves, rotates, scales, and reflects. This creates an interactive demo that shows how matrix math directly affects objects in computer graphics. Through this project, I demonstrated how 3D objects are defined with vertices, how transformations are applied using matrices, how translation, rotation, scaling, and reflection change an object in 3D space, how Python and OpenGL can be used to create interactive graphics. Let's begin with the original object. In this project, I created a simple 3D cube made of 8 vertices, each with an X, Y, and Z coordinate. The cube is rendered using OpenGL polygons and starts at the center of the screen with no transformations applied. At this point, it is completely static and unchanged. Now let's talk about transformations. In 3D graphics, transformations allow us to move, resize, rotate, and distort objects. All these operations work through matrix multiplication, where every point of the cube is multiplied by a transformation matrix to produce a new position. The first transformation is translation, which simply moves the cube along the X, Y, or Z direction. When the user enters values like TX, TY, and TZ, the translation matrix shifts all cube vertices so the entire cube appears to move to a new location. Next is scaling, which changes the size of the object. Scaling factors like SX, SY, and SZ stretch or shrink the cube along each axis. If all values are greater than 1, the cube grows uniformly. If they are less than 1, it becomes smaller. The third transformation is rotation. The cube can rotate around the X, Y, or Z axis using rotation matrices that contain cosine and sine values. When the user enters an angle, such as 45 degrees, the cube turns smoothly around the chosen axis. Another transformation applied in the project is shearing, which skews the object. A shear factor tilts the cube so that its edges slant diagonally, showing how the shape can be distorted without scaling or rotating. During the demonstration, the sequence is simple. The original cube is shown. The user selects a transformation, enters the needed values, the matrix is generated, and the cube's vertices are updated and redrawn based on the new coordinates. Finally, transformations can be combined. Translation, rotation, scaling, and shearing can be multiplied into one composite matrix, allowing multiple effects to be applied in a single step, just like in modern 3D engines.